All right, we are live. Hi, welcome everybody. Thank you all for joining this webinar about the open source Zephyr real-time operating system. My name is Clemens Valens. I work for Elector, and I will be assisting our guest presenter, Benjamin Cabe from France. Benjamin is a developer advocate for the Zephyr project at the Linux Foundation, and so he knows everything about today's subject. Hi, Benjamin. How are things today in Toulouse?
Bonjour. Hi. Thanks for having me. Yeah, well, things are well. The sun is back, and super excited about today's webinar. It was great to see over the past few minutes, how many people we are already lining up in the chat from all over the world. So really looking forward to exchanging with you all.
Yes, quite a lot of people present. Um, yes, as I said, today we will present the Zephyr project. It is a future-proof, hardware-agnostic open source real-time operating system, or RTOS, for embedded applications with limited resources. Zephyr runs on various architectures, including ARM, Cortex-M, Tensilica Xtensa, and RISC-V, and more. There will be a lot of information in this webinar, but don't worry if you can't follow along with the presentation, because this webinar is being recorded and will be available afterwards on the Elector TV channel for replay. So you can watch it as many times as you want later on. At the end of this webinar, you can ask questions. You do this by typing them into the Q&A chat box. A lot of people already found that box. Hi to everybody who said hi in the chat box. Well, I think having that said, because there is a lot of ground to cover, let's get started. Benjamin, the floor is all yours.
Awesome, thanks. So yeah, if you can just put my slides on the screen and we can get started. So yeah, the intro was kind of a mouthful, because there's lots of keywords, I guess, that we will be addressing today. RTOS is one, of course, but we're going to talk about portability as well, and we mentioned several architectures that Zephyr supports. So yeah, let's try and make sure that everyone gets up to speed. Not everyone here, I'm assuming, is necessarily familiar with what an RTOS is in the first place. Yeah, I mean, turns out that Zephyr is actually a really good and really cool open source project that can help you for things like, I mean, those are the typical use cases for embedded and IoT, I guess, but those are also the ones where having a real-time operating system can really help you. And we will see that, I mean, Zephyr, there's many ways to sort of define it, like on paper, at least, it's Zephyr RTOS, but it's in fact more than that. Like if you compare, you might have heard about other real-time operating systems out there. Like you may be using FreeRTOS either directly or more indirectly if you're very familiar with like ESP32 and you've played with expressive devices under the hood. You're probably you might not have realized, but you're using FreeRTOS. There's a bunch of others out there, but I guess the difference with Zephyr is that it will provide you with effectively more than just the real-time scheduler, the thing that helps you move away from I would say, and trying to talk to what I'm assuming the audience is familiar with today, moving away from the sort of the Arduino approach, where you have this super loop where you do everything pretty much in the same task, in the same thread, and trying to get the RTOS aspect of it, which is, among other things, having a scheduler, having the ability to run several tasks in parallel, several tasks that might have different priorities. Some of them might be more critical than others. Like if you're looking at the use case for like worker safety or like healthcare kind of equipment, there are things that your system is going to do that are more important than others. So having the ability to do that, like as an application developer, so that's one aspect of what an RTOS can bring you. But there's more, it helps again with portability, etc., which is what I'm going to try and summarize in this slide, which might actually be the most important slide of the presentation. It's not the prettiest, but what is Zephyr essentially, and what are some of the features? Yes, Zephyr is a scheduler, just like the other real-time operating systems out there. It provides you with the sort of the a kernel, if you will, that's going to help you write code that's more than just a super loop, and code that is effectively multiple tasks that are able to collaborate and to talk with one another. You have a task that takes care of acquiring sensor data for your whatever home automation application, another task that's more maybe in charge of interacting with the file system to store and to log all the data, another task that takes care of connecting to the network, like the kind of things that you would expect from a scheduler. And the scheduler is at a really high level. It's not necessarily rocket science. It's going to save you a lot of time to have one. But what's going to really save you a lot of time is other layers and other aspects of the system and other aspects of Zephyr in particular. One being, sure, you have a scheduler, but you may want to run your application on a variety of MCUs and dev kits and varieties of silicon, right? And so you don't want ideally, you don't want to have to rewrite your application or to port your application when you're moving from an ARM architecture to an ESP32 architecture, et cetera, et cetera. So one thing that Zephyr does is that it sits on top of the existing hardware abstraction layers, the HALs, from many, if not all, the silicon vendors out there. So effectively, Zephyr can already, it runs on STM32, on Espressif, on analog devices, microchip, I mean, you name it. And then it brings you the kernel. And on top of that, it brings, and that's where it's definitely more than an RTOS, just like Ubuntu, if you will, is much more than it's more than Linux, right? It's an actual distribution with lots of applications and services and an entire user experience in terms of helping you install the thing easily. You have the package manager and whatnot. Similarly, Zephyr provides you on top of the kernel with things like that we call operating system services, like APIs for interacting with the file system, APIs for interacting with the display controller, APIs and a model to really have a good abstraction of all the various peripherals that you might be manipulating, right? And again, if I were to do the parallel sort of with the Arduino ecosystem, which I'm fairly certain most of you are familiar with, what I love with Arduino is that there's literally hundreds and hundreds of libraries out there for virtually any sensor that you may be interested in using, like temperature sensor, humidity, whatever. Except that one thing that's sort of missing is that, sure, you will get the code and the driver for the sensor, but it's going to be implementing whatever API. Like maybe for a Bosch sensor, you're going to be calling some kind of API to do get temperature, and you will have this kind of abstraction. For another sensor, for which the driver was written by someone else, maybe the API is going to be get TMP, something like that, and which means that your code, effectively, unless you do something specific, it won't be adapting itself automatically whenever you want to replace the sensor. But after all, it should, because it's going to be a temperature sensor either way. So that's the kind of things that the kind of abstractions that I guess I mean by operating system services and application services that are sort of even higher level sort of abstractions. And even on top of that, something that also interesting with Zephyr, and we're going to go through the sort of onboarding experience and getting started. That's kind of the talk, the point of the talk today. Part of the Zephyr is also helping you source third-party libraries like, I don't know, LVGL if you care about graphical user interfaces, or TensorFlow Lite for microcontrollers if you care about TinyML, helping you basically source the actual third-party libraries that you may be interested in using in your embedded application. Make sure that they actually work well. Make sure that you can easily configure all the compilation parameters, etc., easily, and have everything being really integrated. So that's the whole stack basically that Zephyr is providing you. And part of the stack is, and part of the services, of course, I mentioned a few around like file system interaction, display controllers interaction. A lot of Zephyr is also geared towards IoT. So connectivity wise, like if you care about Bluetooth, if you care about, I think someone was mentioning like Zigbee, Open Thread. I mean, those like all those connectivity 802.15.4 based like sub-gigahertz protocols. That's one of the things where Zephyr is really, really good at, with also really good integration, like across the entire stack, really good integration with all things power management. So all the Zephyr primitives, if you will, and like the Zephyr kernel and the Zephyr services, they're all like collaborating and playing well together, so that whenever your application and your code is essentially doing nothing, and whenever from an application perspective your application is idling, so is the hardware. Like, and we're going to look at some like very basic examples, like blinking an LED, like every second, turning it on, then off for the next second. Like the only power consumption involved there beyond the actual LED is just like, as soon as you want to switch the LED, yeah, it's going to be doing a few things, but then Zephyr and all the peripherals, they all go to sleep basically once there's nothing to do. So we're going to try and illustrate that with some examples. And again, to the point of Zephyr being way more than just an RTOS, just a scheduler, being more like a distribution, it's effectively a complete developer environment. It's going to help you. Like when you get started, you effectively have a way to provision your entire all the tool chains that you may need for whatever target you're aiming for. All the HALs, they're going to be all sourced automatically. You're going to have tools to help you with compiling your code, with debugging, running unit tests, running reports to get a sense of how much memory your application is using, etc., etc. So yeah, that's Zephyr in. I said this was the most important slide, so that's why I guess I spent so much time on it. Zephyr is being used in many, many products, some of which you're not necessarily, you had no idea Zephyr was used in them, but things like, in no particular order, Chromebooks or framework laptops, like the embedded controller, the firmware that takes care of managing the charge of the battery and like whatever happens when the device is the laptop is in standby mode, that's controlled by Zephyr. Wind turbines are using Zephyr, and CAN bus and things like that. The wind turbines from Vestas run Zephyr. You have hearing aids and like all sorts of wearables running Zephyr. You have like watering watering equipment like Gardena. For those of you in Europe, you might be familiar with Gardena, and many, many, many others. So, and I see a quick question in the chat regarding, does it mean that Zephyr is adapted to battery-powered devices? Yes, like very, very much so. You can think and like just a few microamps basically of power consumption for your application when it's again doing nothing, which is usually like most of the time, and that's where like having an RTOS is really interesting. You're sort of scheduling tasks to run at a regular interval, like every 10 seconds, acquire temperature data from an I2C sensor, things like that. Well, when it's not like 99% of the time, what the device will do is basically just sleep, and then just wake up every 10 seconds, wake up the I2C peripheral, wake up whatever code and whatever peripherals need to be woken up, and do the work, and then go back to sleep and go back to just a few microamps of power consumption. So that's that's the products running Zephyr. Whatever dev kit you have in your like on your desk, which if it's like me, you have probably like 10, it probably already runs Zephyr, and we're going to do and see a quick do a few demos of what it basically looks like to get started with Zephyr and do some try a few things. Similarly, just like there's literally hundreds of dev kits already supported out of the box, it's the same for sensors. So it's not in the range of like thousands, maybe like Arduino, but those like hundreds of sensor drivers, they are, like I mentioned before, they are all sort of integrated in the Zephyr like framework, which means that they are all really like interoperable with one another. You have an application that's meant to get temperature data from a temperature sensor. It's really like super easy to replace the like without changing your code. Basically, you will be easily able to adapt. Which and similarly also like what in terms of architecture. We've mentioned, I think, in the intro, some of the architectures that are supported, some of them that are listed on this particular slide. Maybe you've actually never heard of them, but they are supported in Zephyr. Things like Arc and, I mean, MIPS, you might have heard, but it's slightly less popular these days, I guess. But they are all supported. And there's like an entire ecosystem of companies and and an entire open source project, frankly, compared to some other real-time operating systems out there. One thing that's really nice with Zephyr is that it's sort of hosted and lives under the umbrella of the Linux Foundation, which means that sure, the code is in GitHub, just like many other open source projects out there, but there's also like a community of individuals and companies who look after the project and make sure that effectively there is a clear governance and that whatever happens in terms of evolving the architecture, etc., this is done really like in a collaborative fashion, and you would see literally like dozens of new contributors coming to Zephyr every week, which is always interesting to see. So this is getting started today. So I just want to like give you a sense of how to get started, give you a sense of some of the features that maybe you had no idea were just like there, readily available for you to use. Some of those features, they probably show up somewhere on this really tiny and packed architecture diagram. If not, or like if you're not sure, start lining up your questions, and I will be happy to answer if you're interested in knowing whether such or such thing is available. Otherwise, I will also share some pointers in terms of documentation, basically, and how to get and how to learn more. With that, I want to dive into a couple of features that are sort of like some of the things that make really Zephyr different, I guess, from other solutions out there, which might be intimidating at first, but I want to just like mention them, and then we will actually see them in action. One is, and that's one thing that makes Zephyr quite different from things like, again, Arduino to some extent, but also the other real-time operating systems that you might find out there, for which there is really nothing to help you port and integrate with like your hardware easily, which, I mean, some of you might not care at all. Like the only thing you want to do is you have an Arduino, like an off-the-shelf Arduino board, an off-the-shelf ESP32 dev kit, and that's it. Like that's your device. But in many cases, like when you're building an IoT product, you're effectively building your own PCB. And so you might get inspiration from an existing developer kit, but you're going to effectively replace some peripherals by others, some sensors by others, because you're having trouble sourcing them because, hey, silicon shortage. So one thing that Zephyr does and provides is something that's actually inspired and comes from Linux, which is something that's called device tree, where effectively what the hardware is capable of and how you map the hardware to software drivers and software implementations, it's effectively described through something called device tree. And that's where basically for, say, an Arduino Uno, there is a description, and we can look at it briefly later on. There is a file that describes what is the main LED, like the LED 0, say, for an Arduino Uno dev kit. what does it map to? Like, what is the GPIO pin that is being mapped to? And more specifically, this particular GPIO pin, what is the actual GPIO controller that allows to drive this particular pin, etc., etc. All the things that you really don't want to write by hand. Like, it's usually hidden behind the scenes in something like Arduino, or it's not with some other real-time operating systems, and you have to yourself like do the bootstrapping code and the initialization code by like calling all the methods from the silicon vendor hardware abstraction layer and whatnot, and that can be painful. That means that you might have trouble like porting your application from one device to the other, because all this initialization code you would need to write again. So yeah, device tree is actually quite interesting and quite important. We'll see it a bit as part of the demos, and kind of goes hand in hand with device tree is something that's called kconfig, which is really, really powerful in terms of providing you a way to easily, and back to some extent to the is Zephyr suited for battery powered devices and small devices, the ability to really configure what ends up being your final application. Like, what are all there's lots of modules, lots of functionality that is optional in Zephyr, which you may or may not want to use, right? Like, do you want to have logs available in your final application? Do you want to have an interactive shell in your final application? How much memory do you want to allocate to each and every tasks, like, and all that, rather than sort of hard coding things in your code, or like playing with header files and like having hard coded defines in there. There is an entire like configuration management system, which is called kconfig. So that's quite cool. And another thing that's more, again, in the realm of providing you an entire developer environment, something called West, and we'll be using it quite a lot as part of the demos. It's effectively the tool that helps you provision your environment, provision and keep all your dependencies up to date, the Zephyr code base itself, plus all the third-party libraries you might be using, like embed TLS if you're doing network and like HTTPS and whatever communications, etc., etc. So it helps you with that. It helps you with building and like setting up all the like compiling your code, testing it potentially, and it has like lots of interesting like command line options that I will try to demo. So with that, I said that I want to show you basically some tips to help you get started. So one thing that I will do is like a really quick and accelerated version of what it would mean if I were to just start almost from scratch and like get from like blinking an LED, I guess, to something slightly more complex. And the way I would do that, and we can actually switch to my main screen now, I would probably start by going to the Zephyr documentation, right? And that's so docs.zephyrproject.org. And from there, following the getting started guide, setting up my environment. So basically, I mean, Linux is kind of recommended. The Windows, like WSL on Windows, is not too bad, as in like that's actually what I'm going to use today. So it's definitely not bad. You can use the Mac as well. And if you go through all the setup instructions, basically, you will end up installing what we call the Zephyr SDK, which effectively brings you and already provisions pretty much once and for all the tool chains like the ARM GCC and like Xtensa GCC for ESP32 and like all those tools for being able to actually build code. And it's also going to provision like Zephyr itself, like the source code of Zephyr, the source code of all the code samples. And then one thing that this getting started eventually instructs you to do is to run like build your own existing sample application targeting your own existing board. And that's what I'm going to do right now. So you can use whatever IDE you want, or no IDE at all, by the way, or like depends. I don't know if you call Vim or Emacs no IDE, but the thing is with West, usually like you can actually in terms of compilation, you really don't have or don't need an IDE because it's really going to be just literally one line. So let's see. So yeah, I have the entire Zephyr source code in my mounted in my environment. Again, I'm running on Windows, but WSL, so effectively Linux within Windows. And I want to start with what? Running a Hello World, maybe. I think I have it here. So using West, the West meta tool, as we call it, you can build for a given board, targeting like a given board, a given piece of code. And in my case, I want to run a Hello World. The Hello World is really like, that's really all there is to it. And again, back to my sort of what I was saying about like having like needing to bootstrap all the peripherals, etc. You don't see any of that here because it's effectively all taken care of by Zephyr, and you have code that's, I guess, even simpler than the init and loop in Arduino. And so if I were to build this code, which I guess I had earlier, so that's why it's so fast, I effectively built, and I'm targeting a simulator. So I'm actually going to run Zephyr on my machine. And I mean, that's the Hello World. That's maybe not that impressive. But the thing is, I have another device attached to my machine, which is an ESP32 M5 stack device. If I am to build the same app, the same Hello World for it, let's see, I need to, and I will be bringing my camera. Let's see. All right. Yeah, this guy right here. So it's still building. Let's see, linking, building. So I mean, I'm putting it on the screen, but we won't actually see much because the Hello World shouldn't be doing a lot. But let's see. This time around, I'm gonna actually flash the application, and that's also quite nice. Like, because I really don't need, and I think I actually need to turn it on. Maybe let's see. Yeah, I think it's just not turned on. Oh, interesting. Okay, let me just double check one thing. Where is it? I think I turned it off the wrong way. But it's okay because we can actually do a lot with the with just simulator if we need to. Let's see, auto attach. And that's one of the things where actually the WSL stuff can be sometimes a bit painful. But yeah, no, it should be there. Oh yeah, now it is. I think, yes. Not sure what happened. So flashing, and I mean, nothing's happening visually. That's kind of expected, but I can easily connect to the serial output because that's what, I mean, for Hello World. Let's see, there it is. Same code as earlier, except that this time it says Hello World from the actual device. That's nice. Let's see. I think, yeah, we have an LED right here, which is essentially doing nothing. Yeah, thanks for zooming. That's helpful. So going back to the code, this time we're going to build not the Hello World. If we show my screen again, we're going to build Blinky. So same target, except that this time I want to build the Blinky sample. And I mean, this is highly unimpressive to some extent, but what is impressive, I think, is that I can really jump like from one target to the other. And Blinky, by the way, I should show the code because there will be it will be interesting to dig into how it works. But let's see. So finishing up with the build, and then we're going to have a quick look at the code and a quick look also at the the kconfig thingy that I was mentioning. So let's see. I need to flash now. Now it works much better than. And let's see. The LED should start blinking. Yeah, there we go. LED is blinking every second. So okay, let's go back to the screen because the code. I mean, obviously we don't have a lot of time to dive into the code, but I want to give you a sense of like what's the whole device tree thingy, why it's actually really powerful and interesting. What my application is doing. Again, it's a main, right? Like it's not the Arduino loop. It's really like just a main, and I do whatever I want, which effectively is pretty much a loop. I loop forever, and I want to toggle a GPIO pin every second. And this particular pin is something like I'm not hard coding GPIO pin numbers like I would in Arduino, or like the I think like D13 off the top of my head, right? Which is usually the sort of like digital pin 13 for Arduino. No, I'm asking the Zephyr system for a reference to LED 0, which depending on the what device I'm targeting might maybe not exist. It could be the case that the device doesn't have an LED, but if it does, I'm certain that I'm going to be able to toggle it and like to manipulate it as a GPIO. And if I go to my M5 Stack Core 2 device tree definition, so it's a mouthful and maybe as a sort of like as part of this getting started, you might find that there is a lot in there. But the thing is, it's already been done for you, right? Like, I mean, the M5 Stack Core 2, if you have one, then you're not going to have to write the device tree. It already exists. And one thing that that's already there is the definition of what LED 0 should be, which in the case of this particular device is the LED is effectively not directly wired to the SoC. It's effectively wired to another device, another peripheral, like in the M5 Stack Core 2, there is actually a power manager, a PMIC, right? Like a power manager IC, power management IC. And that's this particular device that is effectively, like it's through this device, through this PMIC that I am controlling the LED. And so, but I don't care. Like as an application developer, I want to use an M5 Stack Core 2. It's already supported in Zephyr. The only thing I need to know is that it has an LED 0. Now, if I were to create my own PCB again, and or I would want LED 0 to be something else than the one that's like sort of by default used in the M5 Stack Core 2, then I would be sort of tweaking the device tree, right? Like maybe I'm at my LED 0. This is an LED that I want to actually manually connect to one of the GPIO ports of the device, then I would be changing this. But that's that's kind of the idea. Now, a few more things, because like it's really just like a really quick intro today, and then we will be taking questions. But I've mentioned kconfig. I really want to show you like what it is and how to use it. Basically, there is a through West. I can call menu config west build -t menu config, and I can configure my application, and I can change a whole lot of things, right? Like if I want to enable logging or not. Like by default, let's see if logging is enabled. I think it is, and I should probably use the regex syntax. Yeah, no, logging is not enabled. So if I were to actually connect to the UART like I did earlier, there is outputs there, but there's no logs. If I want to have like actual like debug logs to see what's going on with the GPIO controller, what's going on with the PMIC controller, etc., I would go configure like and enable the logs, and I'm actually gonna do it because I think that's an important aspect of the demo. And I'm going to enable the logs for let's see, for the GPIO. GPIO log level should be debug. Like whenever GPIO stuff happens, it should show up as a trace basically on my UART. And something else that I will be enabling actually is there is a shell in Zephyr, which is really powerful. Oh, it is actually enabled. Let's see. So I'm gonna build my app again, which actually I can directly, if I directly West Flash, it should automatically detect that it needs to rebuild and Flash. And we will have logs, hopefully. I mean, it will still be blinking the LED, but if we connect to the device, and you can see that the kind of like the turnaround is pretty fast, right? Like I'm doing some tweaks, pretty significant ones. Like typically those logs, my guess is that many of you would just like go in the code and add lots of printfs and like recompile, etc. Quick and dirty, except that here it's quick and not so dirty, right? So we saw the logs, right, just before. And we have the shell as well, which is actually quite interesting because there's a lot of things that we can do with this shell. We can get a sense of, this is going to be confusing. I'm going to build another demo that I had, which is going to be strictly for the shell because I really want to show you the shell. Then I'm going to show you also a few more things. And I think we have tons of questions lining up, so I better wrap up quickly, but let's see, the shell, I think you all need to know about the shell. Building it and flashing it in a moment so that we can interact with the system, especially for like troubleshooting, etc., especially also when you're doing sort of like your board bring up phase. You can do really a lot of things. Okay, so this is not the Blinky example this time. It's a sample for playing with the shell, generally speaking, and more specifically playing with the shell when it comes to sensors. So it's a shell as if like it really feels like Linux, right? What are the commands? Typing help to get the help for the commands. Oh, there is a sensor command. There's a sensor command for which I can do sensor info. Oh, that gives me the list of all the sensors that are available as per the device tree, etc., right? So this particular sensor, and you can probably tell that I'm hitting tab and I get also a code completion there. Let's get values from the sensor. And that's like, accelerometer wise, if I flip the device on its side, you can see that the acceleration is sort of like -10, +10, etc. You have other commands for getting information regarding the kernel, right? And like what are all the threads running in my system and how much memory are those threads using, etc., etc. So that's the kind of tools that sort of come for free. And if I'm gonna sort of like disconnect from the device, come for free, yes and no, because probably you don't want to like keep the shell running when you effectively go production, because that may be sort of an attack, like a way for attackers to maybe compromise your system, and maybe you don't want to also waste resources. Speaking of which, there's actually a command to get a sense of how much ROM and RAM my system is taking. And so here I could probably quickly sort of eyeball how much the shell is eating up, which is actually probably a lot, right? Like 4Ks here, 2Ks there. So I would probably want to go back again to menu config and disable the shell, like for the final version of my app, so that I save those resources. So that's that's like really sort of like the getting started. Going further, really just like start playing with all the code samples. Like there's literally tons for all things connectivity, tons also for all things graphical user interfaces, which is kind of like something that like I'm personally a pretty big fan of. I can actually show you the demo of this particular demo. Yeah, it's using LVGL. And I mean, you're going to watch the recording and hit pause, right, if you want to see the commands, but they are effectively taken straight from the documentation. So there's no secret there. But I'm recompiling an application, this time targeting again the M5 Stack Core 2. But this is an app that's going to use the sensor API to retrieve accelerometer data, but also use LVGL. And if we go back to my to the webcam, as it is flashing in just a few seconds. Yeah, it is flashing. Yeah, flashing's done. This app is effectively using LVGL, and it has. And if you were to look at the code, you have like really just a few lines of code just for the like taking data from the sensor, putting it and feeding it into an LVGL chart widget, and that's it. And should you replace the accelerometer, like the BMP, whatever that is, the MPU I have on this device by something else, it would work just the same, or you could use like simulation, etc., etc. With that, you know what? We're already, I think I've done most of the demos that I wanted to show. I can probably pull up a few more slides as we wrap up to make sure that you have all the pointers. But with that, I think we should all go back on camera, maybe Clemens, and start going through the questions, which I'm. And I'm going to be back on camera myself. There we go.
Muted. So,
all right.
I should be
Where should
unmuted now.
Yeah, you're good.
Okay, well, that was very dense, if I can say it that way. A lot of information. Zephyr is clearly very powerful and interesting. We have a lot of questions already. We can start answering one of these. The shell, I hadn't seen the shell myself, actually. Never tried it. It's really powerful, but like you said, it takes up quite some memory, I suppose. So for small microcontrollers, it may be a bit over the top.
Actually, so we need to look in more details, but it's really not that much in the end. I mean, it starts adding up quickly if you, if you were not planning on using UART in the first place, and if you're just going to enable the UART driver just for the sake of having a shell, then things might add up. But no, in my experience, I always use it, and it's not that. It always fits, right? Like it's not that makes my memory overflow or that makes my application not fit. And there are some commands like that are really a must. Like interacting with the sensors through the shell is super powerful. As soon as you do a networking, like on an ESP32 or anything else, really, you want to do Wi-Fi, then you actually have commands for doing Wi-Fi scan and like figuring out the SSIDs that are nearby and like actually attaching to the SSID, the Wi-Fi access point, and doing ping and like NS lookup, whatever. It's it's then you would disable it when you go production, like I said, just even if it's just for the sake of security, because it's probably a good practice to do so. But yeah.
Okay, well, let's answer the first question. We have to answer it always many times during the webinar. Yes, it is. This webinar is being recorded and it will be available on the Elector TV channel later on for replay. So let's move on to a real question. It's a bit of a complicated question. What is the maximum sampling frequency that can be achieved using an SD card in a Raspberry Pi Pico?
Interesting. I wouldn't know or wouldn't be able to give you numbers off the top of my head. So certainly, I'm assuming sampling in terms of like acquiring sensor data. Certainly, like hundreds of hertz, no problem. There's for many, two more aspects to the answer. For many sensor drivers, one thing that's interesting is that there's also support for so-called trigger mode, right? Like you might not, for like an accelerometer, many sensors support, rather than you having to sample quite aggressively to figure out like a spike in acceleration, like to detect that your sensor or like your device was dropped on the floor or like those kind of things, you can instead tell the sensor that you'd rather get an interrupt when a particular threshold is crossed, and then you configure the sensor that way and the driver that way in Zephyr as well, so that you don't really care about sampling at like, I don't know how many hundreds of hertz. You just get one event when the thing happens. So there's that. And another aspect to the question, specifically around Raspberry Pi Pico, is that some of you might be familiar with the PIO thingy in Raspberry Pi Pico, the ability to basically use like a small assembly-like language to create your own like driver that really manipulates all the pins at a really, really low level. And that way you can have like really big and like really fast sampling rates. I think there is actually a driver in Zephyr that uses PIO to drive RGB LEDs where the timing is usually really tight. It does it that way. So yeah, I hope that answers the question. And I should say, like, should any of you actually feel like you need more information or like you have specific questions, we have a really, really active Discord channel. You can, like, one way to get it is chat.zephyrproject.org. Will allow you to just like join it and sign up. There's thousands of people there that are super knowledgeable about many aspects of Zephyr, and there is a Raspberry Pi channel there. There is a sensor channel there, so you can ask questions there too.
Yes, of course. An important thing here also is supposing that you do not make any mistakes in your code and that your code is the best optimized code to sample as fast as possible, of course.
Mm-hmm.
Okay, now a Zephyr question. Is Zephyr a deterministic RTOS?
So there's several schedulers basically available in Zephyr, and again, back to the kconfig discussion and the discussion around Zephyr being like really modular and something you can tweak to suit your needs. So there are several schedulers available. Some of them might have like performance implications, etc. By default, the way that Zephyr works is that it's a tickless scheduler. That's what allows to achieve for something like Blinky, for example, like the sample where we blink an LED. If the only thing that the application does is an infinite loop and you want to sleep for 1 second, and once you wake up, you toggle the GPIO and then you sleep again for 1 second, then effectively the way that the scheduler would be implemented for that is that it would put the actual, like all the peripherals and even the SoC to sleep. If there are more like a collaborative, like multiple tasks, etc., you would need to look into the specificities of the various scheduling algorithms that are available based on your needs. There's also some slides and some like literature out there that provide you, and I think some would provide you with figures in terms of the performance, in terms of how long it takes for Zephyr to do context switching. How long does it take for Zephyr to or for an application or for your code to take a semaphore, to release a semaphore, to put data into a FIFO, etc. So this is all available in the documentation essentially.
Okay, do you have application or product examples from the automotive industry?
That is a really good question. I don't think I have off the top of my head. The one way to answer the question, I mean, you will maybe think that I'm avoiding the question, but it's everything but that. Zephyr is effectively open source, and people don't need to ask for permission to use it, right, to build their products. So sometimes we would know about some applications, some use cases, sometimes we don't. My guess is that it's used. It has to be one way or the other, either for building graphical user interfaces or, but I don't think there's any company that's publicly communicated about it, but maybe some of you watching us today are actually using Zephyr in automotive contests. In which case, feel free to ping us. Essentially, we have a page where we list all the products running Zephyr, and we welcome additions to it. Like you can just send us an email, and we will be happy to add it.
So who is writing the drivers for the sensors? Is that you?
Really good questions. So for it depends. So there's hundreds available. Again, like I said, for sensors like the sensors from Bosch, from STM32, which for some classes of sensors, it's actually like a big chunk of what's available on the market, right? Like for accelerometers, etc. Usually, it's actually them who end up like writing the sensors. Oftentimes, writing a sensor driver in Zephyr is really just it's mostly boilerplate code, and it's and usually the likes of Bosch or STM32, they might already have existing drivers or existing HALs for the sensor. So it's just like basically mapping the APIs one-to-one. But otherwise, I mean, it's the community at large. And usually every week, it's like a handful of new sensors that get contributed. Not all of them might have like sort of the same level of maturity or the same level of integration with Zephyr. What I was mentioning before, like the fact that some sensors might support trigger mode to sort of reverse the flow and have the sensor tell you when something happens. And not all of them might support it. Not all the sensors might integrate all the features when it comes to power management. Like if you have an accelerometer with a power saving mode, maybe the initial implementation available in Zephyr might not support that, but it's usually pretty straightforward to add. So the community plus the vendors, I guess, is the short answer.
Brings me to a question. Is there any quality control of the code, of the contributed code? Is there any testing or?
Yeah, that's an excellent question. So the community is huge. Like there's well over 2,000 people who contributed code to Zephyr since its inception in 2016. And for every major release, which is basically 4 times a year, it's in the hundreds, like 500 plus people contributing code. So we have a process in place where code that comes to Zephyr comes through pull requests through GitHub, and it gets reviewed by the community at large and by maintainers of each area. Basically, like if someone submits a new sensor driver, it would go and it would need the approval of the maintainers of the sensor subsystem in Zephyr. Same for a driver for a voltage regulator, whatever. We have people responsible for this area of Zephyr. So usually the code, I mean, not usually, like the code doesn't get in until enough people have reviewed it, including the maintainers. It doesn't go in until a certain amount of time has passed as well. We want to make sure that everyone has a chance to review the code. And then we have literally hundreds of thousands of tests that run. I mean, not all of them run like for each and every commit, but like if you were to add or contribute a new sensor driver for a particular sensor. One thing that would be checked for sure is that the driver at least and at a very minimum compiles for the 600 plus boards that we support. Like we would try and compile the driver for each and every board and board variation to at least ensure that works. And then we have also sometimes tests that effectively involve, we have the ability to run tests against real hardware. And we have like static code analysis tools that also help spot more like nasty bugs and like, I don't know, like bad copy paste error in a driver or like memory access violation, buffer overflow, whatever. So Yeah, like there was actually like really recently we conducted a study. I don't think it might not be fully public just yet, but just let me just tell you that we had like security experts that dived into the Zephyr kernel and looked for like serious issues like buffer overflows, etc. And they really struggled basically to find just two minor security bugs in the Zephyr kernel, but usually yeah, the quality is pretty good.
Good. It
And
brings us
related, I
nicely
guess,
to
from German.
the next
Yeah,
question.
yeah. Yeah, so kind of related. So mature, yes, like it's. I mean, it's been around for many years now, and even before being open source, some of the code base was already used in commercial products. But and the community and the project and the Linux Foundation as well. Like we are like in the process, especially like this year, you will see a lot happening in terms of providing like actual like aiming towards actual safety certification, providing all the evidence that the development process is mature, like I described with code reviews, etc., and that the code, especially like for the kernel itself, that we the way we effectively manage the requirements and like the way we effectively do all the code coverage analysis, etc., makes like is in such a shape that like it effectively people would be able to go after the safety certification for their products being based on Zephyr.
Sorry.
Nice.
Can
Yeah.
you roll code updates with Zephyr?
Yeah, really good question. So Zephyr works really well with a specific, like a kind of like a dedicated bootloader. I mean, not dedicated, but a bootloader called MCU boot that happens to work really well with Zephyr. So basically, when building your Zephyr application, and thanks to West and thanks to all the tools that are integrated with Zephyr, you would be able to build not only your app, but the MCU boot bootloader alongside it, flash the whole thing to your application, so that effectively when you power on the device, it's MCU boot, like being the first to kick in, then would bootstrap the Zephyr application. But then what that means is that effectively you would have two partitions in your flash, and by default MCU boot would know which one contains your current version of the application. But when your app, you want to update it, basically you would download the new firmware, put it in the other partition, and instruct MCU boot to reboot basically, and switch that way, and like deal basically with firmware update with everything that comes with it, things like signing your binaries to make sure that that they are effectively to be trusted, being able to roll back in case of like any error with your, like, I don't know, your flash is behaving, you want to be able to roll back to the previous version of the application. You could do that as well, and also integrations with existing solutions like the lightweight M2M protocol or Eclipse Hawkbit, for also helping you like with the entire like workflow of what it means to download a new firmware from a web server, etc. So yeah, like not only there is like the bootloader integration, but also there's libraries that are pre-integrated to make it like as seamless as possible. And there's also MCU boot would also allow you to do firmware upgrades using Bluetooth Low Energy, if that's something that you're interested in. I'm sure some of you have played with that, right? Like from your smartphone or whatever, being able to effectively, like, you press the reset button for like 2 seconds, or I don't know, whatever, and then you put the device in a specific DFU mode, and you update it that way.
Okay, we're nearing the end of the webinar. I want to do at least one question about the version numbering.
I'm going to take note of this, maybe confusing. Zephyr SDK is something that you usually install once, maybe you update it like maybe once a year or something, but it's just a way to help you download once and for all GCC and like all the tool chain that you need to actually compile embedded code and embedded code in the context of Zephyr. So that's the SDK. You install it once and for all. And then the other thing that you do once you've done that is you install an actual workspace, which is really where your code is going to live, including the Zephyr code base. And typically the Zephyr code base is 3.6, like the latest release was 3.6, going towards 3.7 when in the summer. But yeah, that's the kind of discrepancy you saw in version numbering. So yeah. So I don't know, like, do you want to come off air or should we keep up with the recording? Because there's some questions that I'm really excited to address, at least by text, once we go off air. But there were some questions regarding footprint, right? Like, in how little RAM, how low can it get on ARM? Think Cortex-M0, basically. So like 2Ks of RAM, I think, is really the bare minimum, and probably something like 8Ks of flash off the top of my head. It's going to give you like a really small app, but yeah, Cortex-M0, if that to give a ballpark figure.
Yes, I think we will have to answer the questions by email or so. There are quite some few questions left, and the longer you talk, the more questions there will be, of course.
Sure, yeah.
So I suggest that we stop here.
Yeah, maybe you can just like for the last minute we have or whatever, just put my the last slide on the screen, just to make sure that people have pointers. Like again, like the last link might be the most important one for going to the Discord, basically, to ask questions. Dietrich is asking about, can I create an embedded web server? Yeah, that's actually that's coming, etc., etc. So yeah, my guess is that the answer to most questions with regards to is Zephyr, like, does Zephyr support X? Usually the answer is yes. Plans to support REST. There is a pull request tracking that. Yep. So I don't know, Clemens, I don't want to like keep you go or keep everyone go over time. So feel free to just wrap it up.
Okay. I will wrap it up then. So we have done yes. As I said in the beginning and at the start of the Q&A, this webinar has been recorded and will be available on the Elector TV channel. Well, thank you very much, Benjamin, for doing this webinar with me. It was very interesting and very inspiring. I think a lot of people you have given a lot of, I think, inspiration to a lot of people to use it, because it is powerful. I would like to thank the public, all the audience, all the people who joined us for attending. I hope to see you again for the next Elector webinar. Okay, goodbye.
Thanks for having me. Goodbye.